Hello, Ralph Matthes speaking. I'm going to present you joint work with Benedikt Ahrens and Anders Mortberg. So it is about a category-theoretic framework for typed abstract syntax. So typed is here the important word. Okay, so we already had an untyped framework. So we had a category-theoretic framework for abstract syntax for systems with binding without types. And now we extend this to simply typed languages. So we had to generalize some definitions. We had to adapt the formalization accordingly. Okay, this was easy. Then we had to extend our existing library of omega cocontinuous functors. And this worked smoothly since we found the adequate abstractions, in particular the right adjunctions there. And we developed a bicategorical framework to analyze the notion of signature functors. And so you may consider this as the fun part. So why do we do it in category theory? We are heading for a characterization of abstract syntax that is totally independent of any implementation. And then we can prove results generically for a whole class of languages, signatures, so with binding. And why is it done in a computer proof assistant? So the theorems are anyway constructive, and so syntax is explicitly constructed, and we exploit this in the formalization. And we can use what the theorem gives us for more combinatorial reasoning about syntax. So there's really a lot of work on formalization of abstract syntax. So we wanted to categorize the work a bit according to our own criteria. Is there a computer-checked implementation of it? Do we have an internal notion of signature? Can we have multi-sorted languages, like simply typed lambda calculus? And what are the features of the theory of the implementation? So this is discussed at more length in our paper. But here just 2 points. So in our work, we have an internal notion of signature. So this is a mathematical object. Don't need meta programming for that. And the strength of our meta theory, so we don't use inductive types. And so we only use a part of the kernel of Coq, and our trusted code base is so much smaller. This was a very important point for Vladimir Voyevodsky, who was one of the fathers of this library. Everything is formalized. So all the results of our paper are formalized. This is done in Coq, but inside the UniMath library of univalent mathematics. So there's a lot of general category theory, but this is also present in other libraries of univalent mathematics also. But we even have a lot of the theory of bicategories available. So our results are expressed by using the notions of univalent foundations. So in particular, sets here are not elements of the sort set of Coq, but sets, univalent sets, are types where we have uniqueness for the equality proofs between the elements. So in principle, the work does not rely on the univalence axiom, but on some of its consequences, such as function extensionality and the existence of set-level quotients. So the new files we added to the library have about 7,000 lines of code, and we had to rework quite a lot of the previous material. let's give us some more view on some of the elements here. So the signatures now for multi-sorted languages. Yeah, so we fix a set of sorts at the beginning. So the sorts are the types of our object language we want to model. There are two notions of signature. First one is just a description of what the language has. So it's totally combinatorial. We take lists of lists over S. You will see this on the next slide. And then there's a semantic notion of signature, which is an endofunctor F from the functor category, from Z to the S to itself, to the same functor category. And Z to the S is the functor category from the flat category of S to the univalent sets. And the endofunctor has to come with a strength. And we provide a translation of this former, say, description style into this semantic style of signature. Let's see this here in the example of simply typed lambda calculus. So we assume we have a function type constructor in S. And so now we index our signature over this two copies of pairs of sorts. And yeah, so we associate, say, if we are on the left side here, we associate to it the arity of the application constructor of simply typed lambda calculus given the two sorts S and T. So the result will be of T, and we have two premises. The first one has the function type S implies T, the second one S, and there's no binding involved, so empty lists here. And to the right-hand side, we get the arities of the lambda abstraction operation for S and T. And so the result type is S implies T, and there's only one premise, and it requires a term of type T with some extra variable of type S. And the semantic signature that is constructed then has this definition. I cannot go into the details, but here you see the elements of the adjunction. So there are the projections for each sort, and then there's this head functor that injects. And the option naturally occurs because for lambda abstraction, there's an extra variable that gets into the context. Sorry. Here we are now profiting for the term monad of the generic results we had before. So this relies on Adamic's theorem, but it's just iterating out of the initial object of the category. And of course, we have to add constantly the identity functor to this F, because we want to add the variable case. Yeah, so here we have omega co-chains, and the co-limit exists if the functor F is omega co-continuous. And so the co-limit has its object part, an endofunctor T over Z to the S. So seen as the sorted terms depending on sorted variables. And substitution for this notion of terms is obtained via generalized Mendler iteration, which also appeared in our previous work in the Journal of Automated Reasoning. And then substitution forms a monad, and also substitution commutes with the term constructors, of course, respecting variable binding. We come to the bicategorical aspects, but only very briefly. So when we construct this semantic functor f, we will have as a building block some, say, also semantic functors f prime, but where here this type is not set to the s, but only s. So this here is not an endofunctor category. The whole f prime is not an endofunctor, and this is this is not so obvious how to overcome it, but still, in the end, it's a matter of types. So we could extend our former formalization quite smoothly. So it's a kind of refactoring. And also working in functor categories that are concretely given, built up from something, is really painful because it's very hard to control the unfolding sufficiently. And therefore, the idea was to treat the problems by passing to a more abstract setting. So where this category is replaced by B, this here by C, and now B and C are just objects of a bicategory. And then these functor categories are replaced by home categories of such a bicategory. And by the end of the day, of course, our prime example are still the small categories, functors, and natural transformations that form a bicategory. Action-based strengths can only briefly be mentioned, although this plays quite a role in the later part of the paper. So it was introduced in the 70s by Paraigis, and Janelice and Kelly put forward another view of actions as strong monoidal functors into some endofunctor category. And strengths for this view, we formulated as parameterized distributivity. And so we show that the strength for our semantic signature is an instance of this concept, and this uses bicategories. And we can even translate parameterized distributivity into specific strong monoidal functors that go into a suitably crafted category. But this will lead to the slogan that parameterized distributivity is homomorphic laws. So it's no surprise substitution was always meant to be homomorphic, but here we have a very general view of this. We come to the conclusions. So it's quite obvious, given the history of this work here, that it pays off to work categorically with respect to a general category, because first we instantiated with the category of sets, and now with set to the S, although a lot of work was still to be done. Then oftentimes results are easier to prove if you have a general category or a general bicategory than if you work in a concrete one or specific one. And then the instantiation to the specific one is mathematical triviality, but it's still not free in the formalization. So we also see that univalent foundations provide a really suitable vocabulary for this formalization work in abstract algebra. This even without explicit need for the univalence axiom. And finally, we think that constructing these term systems still through co-limits is a very nice theoretical way of doing, although we are clear that using inductive types would be more simple for practical use. So I thank you for your attention.
Yeah, let's give a applause around. All right, so we have a remote question. So the question is how painful it is to instantiate this to working over a concrete algebra, say to prove synthetic lemmas over a synthetic type simple type lambda calculus.
Okay, so we did not really develop the theory afterwards then, so we were somehow too happy to have represented the syntax. So unfortunately, I cannot yet say how much work it would be to really do something with it afterwards.
Any question? Oh, okay. We have another remote question coming in. The question is, do you think you could gain something by working with definitional uniqueness of identity proofs and functional extensionality as in the setoid setting?
Okay, so the setoid setting, okay, maybe you think of something even more specific, but when the theoretical grounds were laid for this work here in 20 years ago, we hoped to have at some time an implementation, maybe in Coq, and by that time we only thought of setoid-based approaches. I mean, by that time the only category libraries were based on setoids, and there it was very clear that we would enter setoid hell very early, because you see this whole tower of functor categories. Yeah, they would all live in different levels, and so for me, getting into univalent foundations was the long-awaited breakthrough, so that I could finally do an implementation. This took already such a long time until I could start it. Maybe you would have a better idea there, but for me, the setoids were really the blocking factor for many years.
So let's see. Oh, we have another question coming in. Seems like follow up. So it's a clarification. I meant observational type theory with definitional uniqueness of identity proofs.
Okay. Yeah, I didn't do this, so I mean, we get the functional extensionality just from univalence, but most of the time that this is the thing that drives it. So it's not really univalence. Yeah, it's true, but yeah, maybe one could refactor lots of the theory just in another framework. I could well imagine that, but don't forget the whole bicategorical stuff, for example. I mean, it just needs to be there, and the UniMath library is very rich in that. It's tens of thousands of lines of code there.
Okay. Let's see. I don't see any question locally. I do have a very technical, minor question. So I wonder if you could clarify the construction of the functor H. I forgot which slide it is. For the simply type lambda calculus, I think you mentioned you provided the constructor for the app and lem is the
Yes.
functor H, the disjoint sum of those two.
The functor F is the.
Oh, excuse me, functor F.
Yeah, the functor F is the sum of these, and then there's you have still to add constantly the identity functor to have the variable case. So it's the constantly identity plus these two others. This is the functor over which you form the initial algebra.
Oh, I see. Thank you.
Welcome.
Any other? Oh, okay. We have a local question here.
Yeah. What's the definition of a bicategory in UniMath?
I mean, it's built from many sigma types. Yeah, but they are carefully crafted so as to be manageable. But I mean, a bicategory. I mean, it's a two category with lots of coherence conditions, you may say. It's not strictness. So, for example, if you look at the bicategory of functors and natural transformations, I mean, you have composition of functors that is associative, but in a bicategory, it's not associated. What is it? Associative on the nose, but modulo some associator. I mean, there are natural isomorphisms going back and forth.
You also had a univalent condition, like for categories.
Okay. I mean, there are in the UniMath library, there are all these notions of univalence for bicategories also, but they are not used for what we are doing.
Okay, thanks.
Right. Thank you. And I saw that one more question from in the chat. The question is, can one build term models of dependent type theories in this setting?
Yeah, I mean, this would really be a next step. So, I mean, simply typed doesn't mean the system needs to be only simply typed lambda calculus. So one of our examples is the calculus of constructions in the style of Thomas Streicher, but it's only the raw syntax of the calculus of constructions. Yeah. So we are not claiming to do dependent type theory with what we have here. Huh? But I think at least the whole project shows that you don't need to shy away from having a massive machinery of category theory. So of course we would hope to go further.
Thanks. So for the interest time, any very quick question. Okay, there are no more questions. Let's thank the speaker again.
Thank you.